lecture of birational geometry of Hilbert schemes of points on surfaces, given by İzzet Coşkun from University of Illinois at Chicago. There will be no class for tomorrow. We continue on Friday, the third lecture, and also you are welcome.
So tomorrow morning and 10:30 there is a possibility. Tomorrow morning. The afternoon, in the afternoon there is no class. Yeah, just to fix that.
And you are welcome to ask question. If you want, you can unmute yourself or write down on chat. I will keep on my eyes on the chat, and you can start now.
All right. Good morning, everyone, or good afternoon, depending on where you are. So let me remind you what we talked about last time. So we had X was a smooth projective surface, irreducible surface. We were working over the complex numbers, and what we saw last time that the Hilbert scheme of points, this is the Hilbert scheme of n points, is a smooth, irreducible, two n-dimensional variety, projective variety. And then we discussed that the Hilbert scheme had a morphism called the Hilbert Chammorphism to the symmetric product. And it was easy to understand this, at least said theoretically. What you did is that if you had a scheme, you just sent it to the support of the scheme counted with multiplicity. So you just looked at the length of z at the point pi summed with pi like this. And the other thing that we saw, we understood, so remember the way we started this was as a way of compactifying the configuration space, or like loci of n distinct points on X. And we saw that the complement, which we called B for boundary, if you want. So this is Xn minus the configuration space, or if you want, it's the locus of non-reduced schemes. Locus of non-reduced schemes. We saw that as an irreducible divisor. Okay, so let me remind you about the picture a little bit. If you have n distinct points, right? If you have just nice n distinct points, then you know the Hilbert scheme and the symmetric product are isomorphic, right? But what happens here is that if some of these points come together, just as a way of reminding you what we talked about, like if two points come together, the symmetric product doesn't know the difference, but the Hilbert scheme remembers more information, namely it remembers a little tangent direction, right? So if two points are coming together, then you see that there is a curve that gets contracted under this Hilbert Chammorphism, okay? So that's a quick summary of some of the highlights that we learned last time, that, you know, that the Hilbert scheme is smooth, it's irreducible, there is this Hilbert Chammorphism, and then the boundary, so the locus of non-reduced schemes, or the complement of n distinct points, is an irreducible divisor, and that this Hilbert Chammorphism contracts that divisor. The image of this B, so if you under the Hilbert Chammorphism, the image of this B is codimension 2, where basically two of the points collide. Okay, so that's a quick summary of the kinds of things we talked about last time. So what I want to talk about today is first the ample cone of Xn. So I'm going to talk about this in the case of P2, or maybe P1 cross P1 or something like this. And then, you know, then we will have to introduce more information, a new technique called Bridgeline Stability to be able to do it for more general surfaces. And as we do that, like we will do that in later lectures. Okay, but let's start maybe for some simple surfaces where we can understand this by hand. So the question that you run into is, so let me first explain to you what the ample cone is. So what you can do is you can look at divisors given any variety. So this doesn't have to be the Hilbert scheme now. Like you can look at, say that you have a smooth projective variety Y, and divisors are basically formal sums AI di of codimension 1 subvarieties of Y. So these are codimension 1 subvarieties of Y, right? And then you look at the, free abelian group generated by these codimension 1 codimension 1 subvarieties, and then you can put various equivalence relations on this. Like for instance, you can ask for linear equivalence. So this would be if two divisors are linearly equivalent, right? If there exists a function on Y such that, one divisor is the divisor of zeros and the other one is the divisor of poles, okay? But the equivalence that we are going to put on divisors is called numerical equivalence. And what that means is that two divisors D1 and D2 are numerically equivalent. It's denoted like this. If the following thing happens, if for all curves C, for all curves C in Y, what you have is that the degree of D1, so D1.C is equal to D2 of C. So that their intersection number with respect to every curve are equal. In that case, you call D1 and D2 numerically equivalent. Of course, linearly equivalent divisors are numerically equivalent, but this is sort of more things get identified under this numerical equivalence. And what you do is you form the Néron-Severi space, which is what you do is you take divisors modulo numerical equivalence, this numerical equivalence, and you make this thing into a vector space by tensoring it with R, right? Then you tensor this thing with R to make it into a vector space, okay? So we have this vector space, and now the nice thing about this is that if you look at the set of ample divisors, so here we have our vector space, which is the Néron-Severi space. Again, this is divisors up to numerical equivalence. Then what you can do is each time you have an ample divisor, and let me remind you what ample divisor means. Ample divisors means that if you have a D, then some multiple of that, if you look at all the sections of this OX of MD, then you get an embedding from Y into some projective space for some sufficiently large M, right? And now what you can do, it turns out that being ample is a numerical condition. Like if a divisor is ample, and some other divisor is numerically equivalent to it, then it's also ample. So that what you get here is that you can plot the ample divisors in here. And then what you get is you get a cone. Okay, so here is my cone if you want. And then the first question that we are going to ask is, like, what is this cone? So the question, so what is the ample cone of Xn? Okay? The way you should think about this is that this cone encodes all possible embeddings with the Hilbert scheme into projective space, right? So like the way you can think about this is that, the question of embedding a variety into projective space, is a complicated algebraic geometric question, but by looking at this cone, you can turn it into a question of convex geometry. In fact, this ample cone is an open convex cone, okay? And what turns out what you want to do is that, so let me make a remark. You see, if you have D is ample, if D is ample, right? Then, you see d dot any curve has to be positive, right? Because the way you should think about it is that m times d gives an embedding of this y into projective space, right? And now if you have any curve in here, then you've embedded your curve in projective space, and m times d is the class of a hyperplane. So, you know, this degree of the curve has to be positive, right? So d dot c has to be positive for every curve. This is true for every curve. Sometimes it's easier to talk about the closure of this ample cone, and that's called the Neff cone. So the closure of this ample cone is called the Neff cone. And that the Neff cone, a Neff divisor is just defined. So by definition, so D is Neff if and only if D dot C is greater than or equal to 0 for all curves C and Y. So I will probably occasionally use the word Neff, and what Neff means is that it's a divisor that has non-negative intersection with every curve, okay? And it's a theorem of Kleinman that, you know, the Neff cone is the closed convex cone and the ample cone is the interior of that cone, okay? And the closure of the ample cone is the Neff cone. These are, so the Neff cone is a closed convex cone, the ample cone is an open convex cone. Usually closed convex cones are easier to describe, okay? But of course, there's really no difference between the two. I mean, no difference in the difficulty describing between the two. Okay, so now so this was a little introduction about what ample cones and Neff cones are. Are there any questions about this? If there are questions, remember, you just either chat, write something in the chat, but even better, just unmute yourself and just ask it, okay? All right, so now let's look at P2n, okay? So this is the Hilbert scheme of n points in P2. You see, if you want to understand like something like the ample cone, the first thing that you need to understand is what is the Néron-Sévère space. So in other words, what are the line bundles? What are the line bundles on Xn? Right? I mean, we need to first understand what the line bundles on the Hilbert scheme are if we want to understand, you know, before we even get started on the ample cone, we should understand the Néron-Sévère space. So for this, I will assume that from now on, I'll assume that the irregularity of X is equal to 0. What this means is that if you want, you can take X to be simply connected. So what this means is that I want H1 of OX to be 0, okay? You don't need to assume this to describe the line bundles on Xn, but if you don't have this condition, then the description is more complicated and it's not so easy to say what the line bundles are. Like it's a more difficult question to. So I'm just going, for the purpose of this lectures, I'll just assume this, so that we don't have to worry about certain behaviors that happen, okay? And then there is a description of the line bundles on Xn. So let's think about it. How did we, so let's remind ourselves that we have the symmetric product here, right? Here we have the, Hilbert Chammorphism, right? And this is, you know, the quotient of Xn under the symmetric group, right? Okay, so remember that there is a divisor B here, and the image of this B is some codimension, let me call this thing maybe H, so that we have H of B. So this is codimension 2, okay? So now you see the point here is if I take Xn and I subtract B, right? Then you see this is isomorphic to Xn minus a codimension 2 set, right? I mean, the other thing that I should say is that, you know, when you have a singular variety, right? If you have a weight divisor, if you have a codimension 1 subvariety, so if X is singular, right? It's not true that every codimension 1 subvariety corresponds to a line bundle, right? You have to be a little bit careful because, you know, some Weil divisors might not be Cartier, right? But the point here is that the kind of varieties that we are talking about, if you're talking of Xn here is smooth, and this symmetric product is not quite smooth, but it's, you know, not too singular. It's the quotient of smooth variety by a finite group. So actually, like, even if, like, you know, every codimension 1 subvariety, it itself might not be Cartier, but some multiple is. So it's Q Cartier. So you don't have to worry about, you know, you can compute the Picard group by just, you know, writing down codimension 1 subvarieties, okay? At least, you know, if you want to tensor it by Q or R like we are going to do, okay? The torsion can sometimes be more complicated in these kinds of situations, but, you know, we don't have to worry about that for what we are doing, okay? So now let's think. So you see, if you want to understand the line bundles on the symmetric product, one way of getting a line bundle on the symmetric product is that you put a line bundle on Xn, which is invariant under the symmetric group. So one way that you can do this is that you can pull back a given line bundle from X, so you can do L, let me do it like this. So there pi 1 upper star L tensor tensor pi n upper star L, right? So you take a line bundle L on X and you pull it back to X to the n by every single projection and tensor them, right? Then this line bundle is clearly invariant. Is invariant under the symmetric group, right? So then it descends to the symmetric product. So this way I get a line bundle on the symmetric product, right? And then I can pull it back by the Hilbert Chammorphism. And then in addition, I have this B, which is a codimension 1 subvariety. And so it defines a line bundle on this smooth space so that you see that I have all these line bundles on the symmetric product. Now, under the assumption that Q of X is 0, the irregularity is 0, then there is a theorem of Fogarty that says that those are the only line bundles. Fogarty. So it says that the Picard group of this Xn, right, is isomorphic to the Picard group of X, right, which I get this way, right? You can think of getting the Picard group of X like this. If I have a line bundle on X, I pull it back to Xn by all the possible projections, tensor them together. It's invariant under symmetric group, so it descends to the symmetric product, and then I pull it back by the Hilbert Chammorphism, plus, this B, and there is a little bit of a wrinkle here. It turns out that actually B is divisible by 2 in the Picard group. So but this one is not effective. B over 2 is not effective, but twice at this B is this effective thing that gets contracted by the Hilbert Chammorphism. Okay, so in other words, assuming that the irregularity of our surface is 0, we understand the Picard group, right? And we understand, in particular, we understand the Néron Severi space. But this is fairly abstract. So let's see what this means in the case of P2n. The Picard group of P2, so you see that the Picard group of P2n now should have 2 generators, and then we can understand this fairly concretely, okay? So here is one divisor that I can describe. So here is P2. What you do is you fix a line. Okay? And then what you could do is you could look at the locus, which I'll call H, right, of schemes in this P2n, such that the support of Z intersect this line L. Let me call it L. L is non-empty. okay? The way you should picture this, let me see whether I can get, how do you get colors here? I know that there's a way, oh, here we go. Let me, oh, look at that. So the way you should think about this is that you have like, you are looking at, you know, tuples of n points where n minus one of them are somewhere on the plane and one of them is on this line L. Now, if you think about this, this age is codimension 1 is a divisor, because think of it this way, n minus 1 of your points are free to vary anywhere on P2, right? So there's 2n minus 1 dimensional freedom for these points, but the last point has to vary on this line, so it has only one freedom. So then you see that H has dimension 2n minus 1, which is a divisor here. Of course, this is a really fancy way of sort of expressing like what would happen if you took O of 1. Okay, O of 1 and did this construction. Okay. So this one tells us, so here we get one divisor, and then we have another divisor here, which is B, right? This is the locus of non-reduced schemes. And what Fogarty is telling you is that the Picard group is spanned by H and B, but really B over 2, okay? But, you know, if you're doing this over the rational numbers or over the real numbers, you don't care about this over 2. So the Néron-Severi space, in any case, the Néron-Severi space is the two-dimensional vector space of P2n, is the two-dimensional vector space spanned by H and B, okay? We will usually denote it like this. So I'll put an H in here, I'll put a B in here. And then the question that we are asking is that what is the ample cone in here, okay? All right, if you want to sort of describe the ample cone, you need some more divisors. So let's look at some more divisors, okay? I want to get some, any questions so far? Are the two divisors clear? So one divisor is H, which is you fix a line and you ask that, you look at, you know, n tuples of points such that one of them is on the line. And the other one is B, it's like the locus of zero-dimensional schemes where, you know, you have, typically you have n minus 2 distinct points and one double point, okay? All right. So, but if you want to sort of understand the ample cone, you need some more divisors. So let's make more divisors. Okay. By the way, maybe I should tell you what's the importance of H and B a tiny bit so that you see what's going on here. So in terms of the Hilbert Chammorphism, what's H and B? So remember, we have the Hilbert Chammorphism from P to N to the symmetric product, right? Here, B is the divisor that's getting contracted. So this gets contracted. And H is the pullback of the ample generator. So I have an ample generator, so this has Picard rank 1. So maybe let me call it O of 1 or something like this, right? So this is HC upper star of O of 1 from the symmetric product, right? So these two, H and B, are important, like they are the important divisors that you get out of this Hilbert Chammorphism. But so let's try to get some more divisors to get our hands, you know, if you want to describe these cones, typically you need to make more divisors so that you can get your hands on it. So let's see what we can do. So here is what I want to do. So fix a K, positive integer. And here is what I can do. What I can do is, given a scheme, right, Z, I can look at polynomials of degree K that vanish on Z. Polynomials of degree K that vanish on Z. Okay? And so the way you can write this, you know, the fancy way, like Hartshorne would tell you to write this thing like this, H naught of P2 of I Z of K, right? But what this means is, of course, it's the polynomials of degree k that vanish on the scheme Z, okay? But you see, in particular, this is always a subspace, right, of H naught of P2 of or P2 of K. So this is a fancy way of saying is that the polynomials of degree K that vanish on Z is a vector subspace of the polynomials of degree K, okay? So now the question, so this is polynomials of degree K, homogeneous always, of course, polynomials, homogeneous polynomials of degree K, okay? In 3 variables on P2, okay? So in this way, you see to each Z, I can associate a subspace of this fixed vector space. So this is a fixed vector space. This, of course, depends on Z, right? If I have different points, then the polynomials that vanish on those different points are different typically, right? Okay, so now let's understand. So what's the dimension of H naught of P2 IZK? Well, let's think about it. So polynomials of degree K, so in 3 variables, homogeneous polynomials of degree K in 3 variables, this dimension we know, right? It's just counting monomials, and this dimension is K plus 2 choose 2, right? So now you see, if I have a point, right, and I ask that the polynomial vanish at that point, then that's one linear condition on polynomials, right? To say a polynomial vanishes at a point is one linear condition, right? The way to think about it, suppose that you have your polynomial, so this thing is like ai jk, you know, x to the I, y to the j, z to the k, right? So this is over I plus j plus k. K is bad. Let me fix this. We'll make this, how about we make this? Okay, let me fix this. Let's call this k minus I minus j. Okay. So the polynomial is supposed to have, degree k, right? So a polynomial, every polynomial of degree k you can write like this. And now if you set, you know, if you have a point a alpha, beta, gamma, right? Then you set x equal to alpha, y equal to beta, and z equal to gamma, right? And say that, so, you know, you get the linear equation aij, this wasn't k, let's get rid of it. Alpha to the I, beta to the j, gamma to the k minus I minus j has to be 0, right? So that this is, in terms of once you fix the coordinates at the point, this is one linear equation on the coefficients of this polynomial, right? So to say that the polynomial vanishes at the point is one linear condition. Now, if you are asking the polynomial to vanish on n points, right, that's n linear conditions. So you expect, right, you expect the dimension of H naught of IZ of K to be K plus 2 choose 2 minus n. So that we don't talk about trivial things. I want this dimension to be always positive. Like I want K to be large enough that this is positive. So let's say that to avoid trivialities, choose K sufficiently large so that this number is positive, okay? Otherwise, you know, you run into some trivialities that I don't want to deal with, okay? But so this is what we expect, right? And in fact, if you have n general points, this will be the dimension, right? In fact, if Z is general, then in Xn or in P2n, I guess, the way we're doing it now, in P2n, then this dimension is really equal to this. Okay? And the way you can see this, for instance, is like this, you know, choose your points one at a time. So like the way you do it is like you start with P2, right? You choose a point. If you choose a point, that's a linear condition, so that's good, right? So then you take you take like a section of in H0 of this one point of K, choose a section in there and choose a point not on that section, right? Then to say that you vanish at that point, cuts the dimension again. And then you keep going like this so that you see that each time you cut the dimension by 1. So if you always choose a point that's not contained in a section of H0 of I sort of the previous points, then you see that you cut the dimension each time by 1, so that you see that for a general choice of points, the dimension is really like this. So to make this long story short, what I'm trying to tell you is that you get a map for each K, again, assuming that this number is positive, right? Otherwise, you don't get such an interesting thing, right? For each K, provided that K plus 2 choose 2 minus n is positive, you get a rational map to the Grassmannian of K plus 2 choose 2 minus n dimensional subspaces of a K plus 2 choose 2 dimensional vector space. And what does this map? This map is like this. You take your scheme and you send this thing to the polynomials that vanish of degree K that vanish on that scheme, and you consider this thing as a subspace of polynomials of degree K. Okay? And again, this is only a rational map, right? Because this dimension, because the dimension of H0 of IZ of K is equal to this only if Z is general. What might happen, so why a rational map? Okay, the reason is that for some Z might fail to impose independent conditions. Some Z may fail to impose independent conditions. What does that mean? Let's do an example, right? So if I'm looking at 4 points, so let m be equal to 4, right? So what that means is that, and let k be equal to 2, right? If I look at polynomials of degree 2, this is, so H0 of OP2 of 2 is just a 6-dimensional vector space, right? So now I'm asking for conics that vanish at 4 points, right? Okay, so H0 of IZ of 2, so here is the statement, the dimension of this thing is 2, right? If and only if not all points are collinear. So now what happens is that, you know, if you have 4 points, there are only 2 conics that contain this. What happened to my colors? Up. I will do it pink in honor of Riva. So, you know, if you look at those 4 points, there's a 2-dimensional vector space of conics that pass through those 4 points, and you can write them down. But what happens is that if the 4 points become collinear, then you see what can happen is that then if you look at conics that vanish on that, by Bezout, of course, the line through those points has to be part of the conic, but then you can take any line, right? And then you see that there's a 3-dimensional vector space. If the points are collinear, then the situation becomes, if the 4 points are collinear, then what you get is that H0 of IZ of 2 is actually 3. So that you see that sometimes the dimension of this vector space can jump. That's why you only get a rational map to the Grassmannian here. So far, so good? Any questions? Okay. All right, but nonetheless, you see, I have this map. So we have this rational map from P to N to this Grassmannian. Let me not write the numbers again. And what you can do is the Grassmannian has an O of 1. It has the Plucker embedding. It has the line bundle that gives you the Plucker embedding to projective space, right? Let me call this map maybe phi k. It depends on the degree of the polynomial. And what you can do is you can pull back this OG of 1. Okay? So this gives you a divisor, or it gives you a line bundle on P to N, right? And now the basic state, so, okay. So there are several things that we need to do. One thing that we can do is we should compute the class in terms of H and B. Okay? All right, so let's do it. I claim, so the claim is that the class of this thing, let me call this dk. The class of this dk is k times h minus b over 2. Okay, so if I were to give you, you know, here is our h, here is our b, right? Then we get some divisors here, dk. Okay, they lie in this quadrant if I do it like this. All right, so now how do you prove things like this? I mean, you know, one way to compute these kinds of things is you pair with curves. So let's do it. One way I can do this, here is what I can do, right? So let's do it like this. So here is RP2. Okay, so here is how you should think about it, right? Let's remember what this OG of 1 is. So let's remember how you get the OG of 1. So one way to describe a section, so let's describe a section of OG of 1. So the way you can get, so you have the Grassmannian here. So let's just, let k be k plus 2 choose 2. So here I have k minus n, k, right? What you do, you get an n-dimensional, take an n-dimensional vector space, right? And what you do is you ask for a k minus, so you look, so this is, fix an n-dimensional vector space. Let me say it like this. I'm making a mess here. Fix an n-dimensional vector space. Let me call it lambda. And what you do is you look at the locus. This is called sigma 1 lambda, right? You look at the locus of w in gkn, gk minus n k, right? Such that w intersect lambda is non-empty. Okay? This gives you a divisor in the Grassmannian of planes. It's called the Schubert divisor if you want. And it is what gives the, you know, the Plucker embedding. It gives you a section of this OG1. So, okay, let's think about it. How do I get an n-dimensional vector space? The way you get an n-dimensional vector space is you fix k minus n points. This capital K minus n points, or k plus 2 choose 2 minus n points. So you do that, okay? So I choose, so maybe let me do this thing in a different color. Can people see the colors on these things? It shows up, right? So you fix k minus n points. Okay. And then the question is, how many times does there exist a polynomial of degree k, right? Together with your given, right? So to say that you have this intersection means that I'm looking for schemes. So for schemes of length n, such that there is a polynomial of degree k containing both z and these k minus n points, containing both z and, let's do it, but I think I don't know what this, and the k minus n points. Okay. All right, now we can probe this divisor by curves. So here is a curve that I can take. I fix n minus 1 points, so fix n minus 1 points, right? And then take a line and just slide that line, you know, say slide that point along the line. So I get a curve in the Hilbert scheme, right? I have my fixed n minus 1 points, and I have one varying point on the line. Let me call that curve C. Okay? Everybody get what the curve is? Let me say it again. So you fix n minus 1 points, and you just slide 1 point on the line. Now, if you do that, right? If you do that, then you see that you get a curve in the Hilbert scheme, and that the intersection numbers are relatively easy to compute. Okay, so let's understand what these intersection numbers are. So C dot B is really easy to compute because you see none of those points are reduced, right? These general n minus 1 points are not on that line. So as I vary this point along the line, it's always n distinct points. So this guy is 0. Okay. Now C dot dk is easy to understand as well, because now you see I have k minus n points here and another n minus 1 points, right? So if I look at polynomials of degree k vanishing at these k minus 1 general points, there is a unique curve of degree k that passes through these points. So there is a unique curve of degree k that passes through these pink points and the black points that I fixed. And that curve of degree k intersects this line in k points. So at k of these points, this moving point will lie on that curve. So you see that there are k such schemes, okay? And then C dot H is equally easy to compute. Remember, C dot H was the number of times a point of your scheme lies on a general line. So if I fix a general line, and let me do it with a different color, maybe we'll do it green. So let me fix a general line. The question is how many times a scheme in this curve intersects that line precisely when that point meets that point, that line, right? So then that one is 1. So this tells you already, right, that the coefficient of H has to be K. Okay? All right. Now, if I wanted to do, all right. Now, if you wanted to compute like the other coefficient, you could do a similar trick. There are various things that you could do. What's the easiest thing to do? Yeah, the easiest thing to do would be like this. Now, if I wanted to compute the other coefficients, so what you would have to do is let me find a different curve. Okay, and then the different curve that I can do, I can use the same setup here, right? But instead of fixing n-1 points on the generally, what I could do is I could fix a general point. So I could fix n-2 general points, and I fix one of my points to lie on the line. Okay? Now, if you do that, right? Now you see that this thing becomes k-1, right? Because at this point of intersection of the curve with degree k, I no longer am contained in there, right? Because this curve of degree k will be transverse to that line, and the scheme, when they come together, right, is a point along the line, right? Because the tangent direction is along the line, so that drops by 1. Now there is an intersection with B, right? And C prime dot H is still 1, okay? Now, the only slightly tricky thing here is that knowing what C prime dot B is, and that can be computed actually by Riemann-Hurwitz, and that you see that this is 2. This is Riemann-Hurwitz. Okay? Now, how do you determine this? Like, the way you can determine this is the following. How does Riemann-Hurwitz tell you this? So if you have, right, the way you can think about this, if you have a linear system of degree 2 on P1, how many branch points does it have? And then, you know, this is a map from P1 to P1 of degree 2. And then you see that, you know, that has 2 branch points. This is, you need to do a tiny bit more work than that, but, you know, it still works. This is a case where that linear system has a base point. And if the linear system has a base point, then the intersection with B is with multiplicity 2. Okay? But again, it follows from Riemann-Hurwitz and a little bit of analysis of how the degeneration occurs. And then if you have these 2 curves, you can tell that then the dk has this form. Okay, there are other ways of computing this. Like, you could use it with Riemann-Roch or Grothendieck-Riemann-Roch. You could use other curves, but in any case, we can. The point that you should get out of this is that you can compute these intersection numbers by pairing it with curves, and then, you know, you can explicitly find it. Okay. All right. So now we constructed lots of divisors like this. So let me draw this thing. So here is H, here is B, right? And you have various, for various Ks, you have various rays here. And as K goes to infinity, yeah, you come closer and closer to H, right? So these are the various dk's. But you see, the problem is that this map phi k, right, from the Hilbert scheme to the Grassmannian, right, was only rational, right? So then it does not mean that this dk, so it doesn't mean that dk, so problem, dk may not be ample or effect or even nef, right? On the other hand, you see, if we knew that the map was a morphism, right? If you had the P to N to GK is a morphism instead of just a rational map, right? Then we could conclude that DK is nef, right? And if it's an embedding, then we would get that dk is ample or even very ample, right? So then the question you run into is that when is this map not just a rational map, but a morphism? So now let me tell you the theorem. I mean, the theorem in the case of P2, right, is that, so this phi k is a morphism if k is bigger than or equal to n, if and only if k is bigger than or, and phi k is an embedding if k is bigger than or equal to n. Again, this is not hard. So how can you do this? So like, you know, the point here is this, like, you know, why was this map a rational map and not a morphism? It was because, let's go back, the problem was that sometimes points fail to impose independent conditions, right? So then the question becomes, when does it happen that, when is it? So when does a schema Z, when do all Z in the Hilbert scheme impose independent conditions on polynomials of degree k? And then the answer is that they always impose independent conditions on polynomials of degree n minus 1. And okay, all right. So now let's see, why is that? There are various ways that you can do this, right? So let's look at it like this. So here you have IZ mapping to OP2, and you have OZ, right? So what's happening here is that, so here we have H0 of IZ of K maps to H0 of OP2 of K, goes to H0 of OZ of K, goes to H1 of IZ of K, right? And then it goes to 0, right? To say that this has, so this is always a C n, right? This is the length of the C, right? To say that the dimension of this thing is, you know, to say that the dimension of this thing is big K, K plus 2 choose 2, to say that this has dimension K minus n is equivalent to saying that this is 0, right? So this has dimension K minus n if and only if this H1 is equal to 0. So another way of asking this question is, when is H1 of IZ of K always 0? But you see, the key point here is that you can always give a resolution of this IZ. So this IZ always has a resolution like this. Right? And then you can always see that these numbers BI are always bigger than or equal to n plus 1 if the length of Z is n, and it's equal to n plus 1 precisely when Z is collinear. And BI is equal to n plus 1 if and only if Z is collinear. Okay? And then you see what that means is that now you can compute. So now if I twist this thing by n minus 1, right? In particular, so here, of course, so here BIs are bigger than or equal to n plus 1, and all the AIs are less than BI. So that you see that if I look at the long exact sequence of cohomology, once I twist this by n minus 1, then there is no higher cohomology here. So that says that H1 of IZ of n minus 1 is equal to 0 for all Z and P2n. Okay? Another way of saying this thing is that, you know, like, n points always impose independent conditions of polynomials of degree n minus 1, and they fail to impose independent conditions on polynomials of degree n minus 2 if and only if they are collinear. Okay? All right. So now let's see. So what this tells us that, so in particular, what this tells us is that if I look at phi n minus 1, then I get a map from P to N to the Grassmannian. This now is a morphism, right? So that in particular, if I look at this Dn minus 1, then I claim that this is Nef. It's base point free, right? Right, this is the pullback of O of 1. So it's this map is because its morphism is given by a base point free line bundle. Base point free. And then what in particular, what this means is that this is NEF. Okay. On the other hand, the claim is that it's not ample. Okay, but not ample. Now, why is it not ample? So here is the situation, right? So take your P2, fix a line, right? And put n points on this line, n points on the line. Then I claim that no matter what n points you take on the line, right? The image in the Grassmannian is fixed. So if I have n points on the line, right? So we're looking at, so Z is contained in the line L, right? This is line, right? Then let's look at H0 of IZ of n minus 1. Now, what is this H0 of IZ n minus 1? By Bezout's theorem, right? Any polynomial of degree n minus 1 containing n points on the line has to be divisible by the line, right? So polynomials that vanish on these n points that lie on the line look like L times the polynomial of degree n minus 2. Okay? So in other words, the dimension of this vector space is the same as polynomials of degree n minus 2. So it's given by n choose 2, which notice is the same as, you know, n plus 1 choose 2 minus n. So you get a vector space with the correct dimension, but this vector space doesn't know which n points you picked on the line. So then you see that any n points that you pick on the line gives you the same polynomial. So in particular, you can vary these points on the line and then you would map to the same point. So you see what that means is that there are plenty of curves. So there are curves. In fact, this locus is an n-dimensional space. So there are curves in P2n, right, that get contracted to under this map phi n minus 1. Curves in P2n that get contracted, under phi n minus 1. Okay? All right, so now I claim that this now tells us what the ample cone is. So then the theorem is like this. The ample cone of this P2n is the cone spanned by h and n minus 1 h minus b over 2. Okay, so let's maybe draw the picture. Here is h, here is b. Let me just draw it here. This is n minus 1 h minus b over 2. Okay, and then the ample cone is, we are saying, is the interior cone here, is the open here. Or if you want, the NEF cone is the closed cone. Okay. Now, why is this? The reason is like this, right? We already know that h and n minus 1 h minus b over 2 are NEF divisors. They're base point free. So in particular, they are NEF, right? They give a morphism to project a space, so the degree of any curve, like they give a morphism to project a space, so the degree of, and they are the pullback of O of 1 from a projective variety, so that, you know, under a morphism, so you see that, you know, the degree of any curve has to be non-negative, right? But on the other hand, each of these contract the curve. So there exists a curve. There is a curve such that, I mean, there's a curve C1 and a curve C2, I should say, such that C1 dot h is 0 and C2 dot this one is 0. So in particular, these things cannot be ample, right? If they were ample, the degree of any curve would have to be positive. So these things are nef, but not ample. So they have to lie in the boundary of the nef cone, right? And if you want to describe a cone in a two-dimensional vector space, you just need to say the two boundary rays, right? So that you see that the nef cone is precisely this and the ample cone is the interior. And what are these curves that get contracted? So remember, age was the one that was giving the Hilbert Chammorphism, right? The Hilbert Chammorphism to the symmetric product, right? So this curve C1 is fairly clear what you need to do, right? You fix n minus 2 points, fix n minus 2 points. And then what you do, you fix another point, but then, you know, there is a one parameter family of length 2 schemes there. So you take the curve as the curve that just varies this tangent direction. So you see that C1.age is 0, or this is the curve that gets contracted under the Hilbert Chammorphism, or if you want to see it directly, if I fix a random line, right, it won't contain these n minus 1 points. So none of these schemes actually intersect this age. So that you see the C1.age is 0. And here, remember how this guy was given. This guy was given by the map P to N, mapping to this Grassmannian Gn minus 1. So I look at polynomials of degree n minus 1 that vanish on this, and I just described for you what are the curves there. What you can do is you fix a line and you just vary n points on that line however you want. In fact, if you take any curve in that space, right, that gets contracted to a point under this map, because the polynomials of degree n that vanish on that scheme are just those that are divisible by the equation of the line, okay? So this tells us the ample cone of the Hilbert scheme of points. All right, let me take a little break and ask for questions. Are there any questions with this, about this? Maybe I should wrap up this discussion by saying that you can use the same technique to compute the ample cones of Hilbert scheme when X is, you know, more complicated surfaces like P1 cross P1, a Hirzebruch surface, you know, Del Pezzo surfaces. Here I'll say degree not equal to 1. The degree equal 1 case, you need to do more work. Okay, so if the degree is not 1, you can compute the, so you know, you can use the same technique to compute the ample cone of the Hilbert scheme for these kinds of surfaces. If you want to do it for more general surfaces, we will need to talk about Bridgeline stability, which is what I'll do, you know, at the end of the third or in the fourth lecture. Any questions so far?
There is no question in chat so far.
Okay. So anyway, if you have questions, just scream, unmute yourself and tell me. So the next thing that I want to talk about is the effective cone of P2N. Okay. So now you see, if you talk about divisors, right? Divisor is a formal linear combination of codimension 1 subvarieties. So say that you have a projective variety Y smooth, right? It's a linear combination of you know, codimension 1 subvarieties. And then the question that you can ask is, when can you make all these AIs be non-negative? For which divisors D, for which D is AI, well, can you make? Okay, so let me ask you sort of, in the case of P2N, this is a fairly concrete question. Maybe let's do a few examples to see what we're talking about, right? So let me start with n equals 3, okay? This is P23, right? Say that I have 3 points, right? What divisorial conditions can you put on these 3 points? What's the most special position? What is the most special divisorial condition? on 3 points. And of course, everybody knows the answer, so somebody should shout the answer. Okay, now don't be shy, tell me the answer because you know the answer. Like, in what positions, like what is the most special divisorial conditions the 3 points can be in the plane?
They can all be the same.
That's not divisorial, right? That would be a two-dimensional thing.
They all lie on a line then?
They lie on a line, right? So if I take, let me just look at this. I like these colors. So if I make my 3 points lie on a line, right, that's a divisor, it's codimension 1, right? This P236 has dimension 6. So, you know, the 2 points, the first 2 points you pick is no conditions, right? Then there's a unique line joining the 2 points, and you're asking that the third point lie on that line is one condition, so that the locus of collinear points is dimension 5, and it's a divisor. And you see, this is the most special condition that it can be because, like, you know, I claim that. So here is, again, our picture. So here is our H, here is our B. So we know what the ample cone here is. That's 2H minus B over 2, right? Okay, so I mean, we'll figure out what the class is. So let's find the class of the collinear points. So here is what I want to say. You see, here is what I can do. Right, let's do this. So let me take a P2. Let me fix a conic on this P2. Fix a conic, right? Irreducible conic. And look at 3 points that vary on that conic. So make 3 points vary on that conic. All right, so this is really a P3 if you want. But you know, like take a curve in there, your favorite curve, right? Take a one parameter, take a pencil in this OC, you know, OC of these 3 points, right? The point is that for like these 3 points are never collinear, never collinear, right? If these 3 points ever became collinear, right, then you would violate Bezout, right? There would be a line that intersects this irreducible conic in 3 points, right? So no matter how I vary these 3 points on this conic, these points never become collinear, right? So what that means is that in particular, I can compute the class of this divisor at least up to a scaling, right? So if I take so you know, if we take a curve like this, right, C dot H is 2, right, and C dot B is 4, so that you see that right, so that you see that the class of the divisor of collinear points is given by H minus B over 2. It's some multiple of this. I don't care about the multiple. The ray, it lies on this ray. I mean, we can determine the multiple, but I don't really want to know the multiple, okay? And now to say that this is the most special divisorial condition means that the effective cone, right? The cone of effective divisors of P23 is just the span, is the cone generated, so the effective cone of P23 is generated by this H minus B over 2 and B. Okay, what that means is that, like, you cannot have an effective divisor further to the left of this ray. Okay, now why is that? And I gave you a proof of that, right? Suppose that you had the divisor, said that there was a divisor such that it was of the form alpha H minus B over 2 with this alpha less than 1, right? Then you see if you do the C dot D, right, we would get a negative number, right? Because C dot H is 2, C dot B is 4. So, you know, if this alpha is less than 1, then this number would be negative. But you see, like this is so here is the situation. So maybe before I give you this proof, let's just say, suppose you have a Y, irreducible variety, and you have a divisor on this, okay? So you see, this effective divisor is extremal, right? If you have the following property, if you have a moving set of curves, right? So if you have a set of curves that cover sort of an open set in Y and are disjoint from D, right? If that's the case, you see, you cannot have, like, you know, if I wanted to subtract a small ample divisor from this D to get still an effective divisor, then you see you would run into the problem that any such curve that this would be negative, right? But the problem with that is that if this were effective, right, then, and you had the covering family of curves, you see any irreducible curve times any effective divisor is non-negative unless, so this irreducible curve, this is effective divisor, unless, right, C is contained in D. But you see, if these curves are covering your Y, they cannot be contained in this fixed effective divisor. So what that means is that, you know, if I give you a moving set of curves that are disjoint from this effective divisor, right, then what you end up concluding is that that has to be the most special or an extremal such divisor, okay? And now you see I've just done this because, you know, given 3 points in P2 that are not collinear, right, I can find a conic and then vary those 3 points inside that conic. And we just said that those never become collinear. And these were general 3 points, right? So you cover these kinds of curves, cover your Hilbert scheme, but they always have intersection 0 with this collinear, the divisor of collinear points. So you conclude that the most special divisorial conditions in 3 points is really these, this divisor of collinear 3 points. I should always point out that B for independent, like B is of course very special. So I should have said that B is an extremal divisor. B is an extremal divisor. Again, you can see this very easily, right? If you take, you know, we already saw this. If you take and you fix n minus 1 points and pick a random line, right? Whoop, what did I just do? Pick a random line and move this point around, right? This kind of curve never intersects B, but these kinds of things clearly cover an open set in the Hilbert scheme, right? If I take any n general points and fix a random line through a point that misses the other points and vary like this, you get the curve that passes to that point. But such a curve that B is 0 because none of these schemes become non-reduced, right? So that you see that B is always an extremal divisor by the same argument. So when I describe the effective cone, B is always an edge. And the interesting question is finding this edge, finding the edge on this side, not the B side, okay? And in the case of 3 points, we've just did it. We see that the divisor of collinear points together with the divisor of non-reduced points span the effective cone, okay? Now, the next question that I want to ask with n equals 6. If I have 6 points, what's the most special codimension 1 configuration that 6 points can be in? Again, you know the answer, so somebody should tell me.
Lie on a conic.
Yes, they lie on a conic. Again, you know, if you have 5 general points, right? Let me see whether I can do this. If you have 5 general points, right, then they determine a unique conic typically, right? And to say that the 6th point lies on the same conic as a codimension 1 condition, you require that this point be on this curve as opposed to a random. And again, by a similar argument, right, you see that this is the most special. So you can see that this is the most special configuration. Again, you play the same game. Now let me fix a cubic right? Fix a cubic and take 6 points on that cubic. If you take that 6 points on that cubic, you see a cubic is an elliptic curve. So like you have these 6 points, right? So I require that this is not OE of 2, right? I mean, again, if you chose your curve, like the line bundles on that elliptic curve come, you know, are, you know, it's self-isomorphic to line bundles at degree 6, or it's self-isomorphic to the elliptic curve, right? OE of 2 is a single point, so you just choose 6 points, so you don't get that point. Now, if I do this, and I vary these points within that linear system, you never, these points never lie on the conic, right? And this is a general set of points. So you see that this is a more special configuration, okay? So this tells you the effective cone when you have 6 points. And now, of course, you can see the pattern. Suppose that I said 10, 15, no, 10, 15, and so on and so forth. If I have a triangular number, if I had 10 points, what would you tell me the most special configuration was? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. By now, hopefully people see the induction. So what's the answer?
Lie on a cubic is that?
Lie on the cubic. Right, 10 points typically don't lie on the cubic, 9 points determine the cubic. To say that the 10th point lies on the same cubic is codimension 1. And again, by a similar argument, you see that that's the most special possible. When I had 15, that would be those that lie on a quartic and so on and so forth. So this at least tells you the answer when you have a triangular number, okay? The next interesting case, oh, by the way, I should have said that, you know, when n equals 2, 3, 4, 5, 7, 8, or whatever, we can play similar games to find, you know, to find what the divisor is. You just tweak the construction a little bit. The first interesting case is when you have 12 points, okay? So now suppose that I have 12 points, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And again, ask me what is the most special? What is most special? Codimension 1 condition that 12 points can be in. All right, what's the answer now?
Is it 2 sets of 6, both lie on conics?
All right, so here is one guess. I could have that I have 2 conics and I want like the 6 points to lie on those things. But you see, that's not codimension 1 because 5 of the points determine the conic. So to say that the 6 point lies on that is codimension 1, except that if you ask that to happen twice, right, then that's codimension 2. So that's not a codimension 1 condition. Just like, you know, you could ask that all 12 points lie on the cubic, right? But that's codimension 3. There are many conditions that you can put on these things, but what we want is that it be codimension 1. So other guesses? No other takers?
There is a guess on chat.
Oh, that's the same guess as before. All right, so now let me tell you the answer and I'll end there and I'll tell you the answer in general next time. Oh, so Justin is suggesting something good. So you could ask that 10 of the points lie on the cubic, or more generally, you could ask that, like, you could play games like say that 3 of the points lie on a line, or 6 of the points lie on a conic, or 10 of the points lie on the cubic. These are all very good guesses. It just turns out that they are not the most special. They are not the extreme array, okay? So let me tell you what the answer is in this case. And then we'll discuss what the answer is in general next time, which will be Friday, by the way. So here is what I want to say. Let me take the tangent bundle to P2. Okay? Let me take the tangent bundle to P2 and let me twist this thing by 2. Okay? So let's look. How do you think of the tangent bundle of P2? It's given by the Euler sequence, right? So I have O goes to O of 1 of 3 goes to the tangent bundle of P2. Okay? So the tangent bundle of P2 has 8 sections, but if I twist this by 2, so then I get O goes to O of 2, goes to O of 1, O of 3 goes, sorry, this is my daughter ringing the doorbell. Hopefully she won't keep doing it. All right, so this is O of 2 goes to O of 3 goes to T tangent bundle of P2 twisted by 2. So let's compute H naught of this thing. H naught of O of 3 cubics, they're 10-dimensional space with cubics. So if you have 3 of them, this is 30-dimensional. Quadrix is, conix is 6-dimensional. So you see that H naught of this is 24-dimensional. This doesn't have H1. So you see that H naught of TP2 of 2 is 24-dimensional. Okay, so let's think about what we did. Let me go back a second, right? Now, what does it mean for 3 points to be collinear? So for 3 points to be collinear, you see, it means that you have O of 1. How many sections does O of 1 have? It has 3 sections, right? We were looking at points or schemes that failed to impose independent conditions on O of 1, right? So to say, if you had 3 random points, then there were no lines that contained them, right? So this divisor that we talked about, the divisor of points on the line, so D was those points that failed to impose independent conditions. On O of 1, on sections of O of 1. Similarly, when we talked about this, right, conics are sections of O of 2, right? So those that lie on the conic, the 6 points that lie on the conic, or the schemes that lie on this conic, are those that points that fail to impose independent conditions, fail to impose independent conditions on O of 2. You see? And similarly, you know, if you think about these, those that fail to impose independent conditions O of 3, O of 4, and so on and so forth, right? Now, when I come to n equals 12, I can no longer build this thing with a line bundle. What I have to do it is with a vector bundle. Now, you see, you have 24 sections here, right? So if you look at 12 points, so, you know, if you had 12 points, the 12 points, right? Typically, you know, if you ask that the section of a rank 2 vector bundle to vanish at a point, right, it should be codimension 2 conditions, right? You have a 2-dimensional vector space and you have to pass to the 0, right? So that should be 2 conditions. And so if you ask that to happen over 12 points, that should be 24 conditions, right? So typically, I don't expect any section of TP2 of 2 to be able to vanish on Z unless it's 0, right? And now I can define the divisor, so let me just call it TP2 of 2, as the set of points Z that fail to impose independent conditions on, let's say, TP2 of 2, all right? And now I claim that this is actually the most extremal position that 12 points can lie in, okay? Now it's a little bit harder to see what that means, right? So in other words, now I have sections of this tangent bundle of P2, or twist the tangent bundle of P2, and now the condition that I claim is the most special is that they fail to impose independent conditions, okay? Now, this is a little bit trickier, for there are several things that you need to check when you do this. One is that you need to check that this is really a divisor. Is a divisor, okay? I mean, the danger here is that it could be all, like it could be that every 12 points fails to impose independent conditions, right? And of course, the next thing that you need to check is that it's extremal. But the key point that I want to bring out here, and I'll stop here, is that, you know, if you want to understand the effective cone of the Hilbert scheme of points, it's no longer enough to just think about line bundles. What you need to talk about is higher rank bundles. So next time, what I'm going to do is I'll introduce higher rank bundles, moduli spaces of higher rank bundles on P2, and describe for you the effective cone of Xn or P2n, right? P2n, okay? So that will be the next lecture, and we'll talk about like how the geometry of these higher rank bundles interact with the geometry of the Hilbert scheme. And that will take all of the next lecture. And then the final lecture will be, I'll introduce another technique, which is called Bridgeline Stability, which will be a way of sort of repackaging and like extending the kinds of games that I'm doing here by just drawing pictures and things like this. So this is where we are headed. And let me remind you that next lecture is on Friday. So there isn't a lecture tomorrow, and the one after will be on Saturday at the same time. So let me stop here. And then, as I said, I'll say a lot more about this example as to why it's a divisor, why it's extremal, and sort of describe the general picture. All right, let me stop and see whether there are any questions.
Okay, thank you so much. Is there any question? I think so far, no. You can unmute yourself or write down the chat. Okay, I think there is no question.
All right, so then, you know.
Thank you so much for lecture.
Friday.
See you on Friday.
Okay.